Here come the lights. Watch your eyes. Good day. How is everybody today? A little shout out to everybody down south. That wasn't quite right. But anyways, let's have some fun with it. So today, folks, what we're going to do, systems of inequalities. You've seen this before. You know, all of this is stuff that you've done in Algebra 2 and previously. We're going to throw a little bit of a twist on it today in that now we're going to deal with some nonlinear equations. So we're going to throw a parabola in, we're going to throw a circle in, that kind of stuff, and some other funky lines that you might not remember, but good to review. All of this is coming together for a reason in the next section where we're going to be using this for a thing called the corner point principle to figure out a thing called linear programming. So we'll get to that. But for today, systems of inequalities. So first things first, we've got a standard form equation here of a line, right? Now, there's two ways we could graph this. We could go ahead and solve it for y equals mx plus b, or we could graph it with intercepts. Remember, we've got those two choices. So first, let's do it with intercepts, and then we'll change it to y equals mx plus b, because there's something important we want to see there. So if we do intercepts, let's make this our purple graph. We're going to do an xy chart. And remember, intercepts are when the other variable is a 0. So the x-intercept is when y is a 0, and the y-intercept is when x is a 0. That's all it is, right? If you're here, you haven't gone up or down any, so your y value is 0. That's your x-intercept. And if you're here, you haven't gone left or right any, so your x value hasn't gone any. So all we've got to do now is decide, well, what x value makes y 0? So if y is a 0, it's not there. So if we think of that as an equal sign, what value of x would make it 1? Right, 1. You can check it. 1 minus 0 equals 1, so that would be right up to that point. We'll talk about the or equals and inequality in a moment. Secondly, if we put a 0 in for x, now we've got negative y is 1. So what the opposite of what number is positive 1? Right, the opposite of negative 1 would be positive 1. So we get that. So if we go to graph this, the thing about graphing inequalities that we have to remember is there's two parts. There's the part about line style. Is it solid or dashed? Meaning if it's solid, it equals the line. The line itself, like when we do an equation, the line itself is the solution. But with an inequality, if it's not equal, that means it's right up to the line, but doesn't touch the line. The line itself is not a solution. So to show that, we use a dashed line. A dashed line means it's right up to it, but not quite there. It's kind of like when we graphed inequalities on a number line, and we used a open or solid dot. When we had the open dot, that meant it was right up to the point, but not including the point. The solid dot meant it included the point. So we go ahead and plot these points. X is 1, y is 0, right there. X is 0, y is negative 1, right there. We're going to get, let's put in a couple more points. Right about there, right? And dashed line. That's going to go forever in both directions. Next, the second part is we have to decide which side of the line is our solution. Because this is saying that the x minus y is greater than a 1. Well, what does that mean? Well, there's two ways to do this. In this case, when we're in standard form, we're going to use a test point. So we're going to choose a point that's obviously on one side or the other of the line, and then what we're going to do is see if it's true or false. If it's a true statement, it means your test point is in the solution region, the area that should be shaded. If it's a false statement, then your test point's not right. It shouldn't be shaded. Shade the other side of the line. Okay? So let's try an obvious point, the easiest one, usually the origin, 0, 0. But sometimes if your line's going through that point or really close to it, and you can't really tell from your drawing, choose something easier like 1, 1 or something like 3, 0, something way off so that it's obviously not on the line itself. So 0, 0, the origin is definitely not on our line. So if we put a 0 here and a 0 there, we get 0 minus 0, which is 0. Now, is 0 greater than 1? It's not, is it? So that's a false statement, which means our test point is on the wrong side. We should be shading the other side. So that's what we're going to do. We're going to throw a little shading in over here. So if we were just graphing a single inequality, and that was it, that would be our graph. It'd go forever, all the way out, right? Now, we're going to go ahead and do this with a system of inequalities, which means more than one. So now let's deal with this one. Now we've got our conic in there, a parabola to be particular. And if we remember our parabolas, for now, treat this as an equal sign. Let's just find the graph, okay? Let's make this our green graph. So, I forgot. Let's back up to this one. I wanted to show you if we change it to y equals mx plus b. Let's do that really quick. So let's go ahead and subtract x. Negative y is greater than negative x plus 1. Then we've got to get rid of that negative, right? So let's divide by negative 1. And since we divided by a negative, what do we have to remember about inequalities? We have to reverse the inequality. Change directions whenever we multiply or divide with a negative on both sides. So this would become y is less than positive x minus 1. Now again, take a look. The y-intercept is negative 1, and the slope is positive 1. So up 1 over 1, up 1 over 1. It's the same graph. We still did a dashed line, but now when you have y equals mx plus b, when y is by itself, you can read the inequality to determine which way to shade. When y is all isolated by itself, it says y is right, less than. So if y is less than, that would mean shade below. So I keep saying shade below or above. We always want to think of it that way. There's one case at the end here where we're going to think of it the other way, and I'll show you why we don't want to do that. Think about this for a second. If y is less than, and you thought of that as left and right, which way is less than when it comes to left and right? Correct. Left would be less than, which means we'd be shading this way, which wouldn't be correct. You can try a point in there and find that's true. It wouldn't be correct. So whenever you read it, above or below. You're always thinking of it as above or below. Okay, now let's get to our parabola here. Our parabola has a y-intercept of negative 3, a parent shape opening up, parent shape being 1 for the a value here. And so we can go ahead and just plot that 1, 2, 3 right there. It opens up, so remember a parabola over 1 up 1, 1 squared is 1, over 2 up 4, 2 squared is 4, and over 3 up 9. It'd be kind of way up here, wouldn't it? Backwards 1, negative 1 squared is positive 1, up 1. Backwards 2, negative 2 squared is up 4. And backwards 3, negative 3 squared would be up 9, also way up here. Now notice that one says y is greater than or equal to. What kind of line style do you think we're using? Right, solid. This time it's solid. So it's going to go through, and it's going to go through. Now, before we shade, I want to ask you this question. Which way do you think it's going to go? Above or below? Above or below? Y is by itself, so we can read it this time. Y is greater than. We're going to shade above our graph. Now again, think of that. If you thought of it as left and right, which way is left or right of a parabola? I mean, there, left or right of that line, or right? Above or below. So, y is greater than, we would shade above. And so on. So notice right now with our two equations, we have double shaded right there. That would be our solution region for this system of inequalities if those were the only two. The one thing I want to point out here is there and there we're intersecting, aren't we? So my question about that is, would that be a solid dot or an open dot? You have a solid line and you have a dashed line. So one of them includes the point, and one of them is right up to the line and isn't being included. So which do you think it is? Right. if you said open dot, you are correct. These would intersect at open circles. If they were both dashed, open circle, not included either line. Only would be it would be a solid dot if they were both solid lines. If they're both solid lines, then that would create the solid dot intersection there. Okay, so now we've got that going on. Let's take a look at this problem. And let's include it in the same thing. The reason I'm doing more than 2, even though your homework will mostly only do 2, is because the next section, we're going to do multiple ones on the same graph to deal with that linear programming idea. So we've got to get used to this. So let's go ahead and go to a blue line now. Now notice y is less than -1 could be thought of as y equals mx plus b. You think of it as y is less than 0x minus 1. There's no x value there, so that has to have a 0 in front of it to make it not there. And that would mean the slope would be 0. And I know those of you who've had me in algebra remember me talking about slopes being 0 versus undefined, right? Undefined, superhero, never mind, I'll get to that later. But 0, that's just flat. That's just walking on the ground. You could do that all day long. That's a 0 slope. There's no slope to that. That's a crazy slope. That's no slope. So y is less than -1 really is a line that's flat right here at -1. It's dashed because it's not equal to. And again, at these intersections, we have a dash intersecting a solid. Those are open circles at those intersection points. Now again, above or below. Which way are we going to shade this one? Y is by itself, so we can read it. Y is less than. Which way does that go? Less than is below. So we would be shading all of this stuff. And now we have 3 equations, or inequalities. We're looking for triple shading. Now we're limited to just this zone. That's only got double shading. Singles, singles, singles. So down to here. The last one I want to talk about is kind of an oddball. It says x is less than or equal to 1. So we know what kind of line it's going to be, solid or dashed. Right, solid, because it's or equal to. That includes the line. That does not, that does, that does not. Now, x is less than or equal to 1. We can't write that as y equals mx plus b because there is no y. We've never learned about an x equals mx plus b because there is no real thing that we ever think of that way. So we can't really define this as y equals mx plus b, which means that slope is undefined. That's our straight up and down slope. Because it's undefined, you can't define. That's a number divided by 0. That's a rise of however many you want and a run of none. So a number divided by 0. So this actually is a line that's vertical. Since it's at 1 and it's solid, it's going to be right here. And this is the one time we don't think of it as above or below. Because how do you think of above or below a vertical line, right? You can't. So this is the one time we think of it as left and right. So which do you think x is less than would mean? To the left or to the right? Less than on the number line? Yep, to the left. So we would shade all of this. And what I want you to see is that right here, even though, okay, hold on, right there, we have an open circle again, right? Because that's a solid meeting a dashed, but right there, that's a solid hitting a solid. That's a solid intersection. In the last detail, since we had 4 equations, we're looking for the quadruple shading. I know it's a little complex here, or it's a little muddled, but I'll make it more clear for you. Above the parabola, to the left of the pink line, below the blue line, and, oops, that was too much up here. because we also have to be below the purple line. Right there. There's our solution region. Okay? So the reason this is important, like I said, linear programming, you're going to graph to find those intersecting points. And that's going to become important because those specific points are going to tell us the answer to problems that we're going to solve having to do with maximizing and minimizing things, such as crop values and profit and loss. So, until next time, I suppose I should tell you, watch your eyes. There go the lights.